Space is big, really big. It's an almost unfathomable expanse that stretches beyond our imagination. It's filled with billions of galaxies, each containing billions of stars. These stars are scattered across the universe, forming intricate patterns and structures. Stars are the building blocks of galaxies, illuminating the cosmos with their radiant energy. They are the beacons of light that guide us through the dark expanse of space. They are massive balls of hot gas, primarily hydrogen and helium, held together by their own gravity. This gravity creates immense pressure and heat at their cores, igniting nuclear fusion. These celestial furnaces are responsible for creating the elements that make up everything around us, including ourselves. Through the process of stellar nucleosynthesis, stars forge elements like carbon, oxygen, and iron. Understanding the life cycle of a star is key to understanding the universe we live in. From their birth in stellar nurseries to their eventual demise, stars undergo a fascinating journey. Stars are born, they live, and they die. Their birth begins in vast clouds of gas and dust where gravity pulls material together to form a new star. Their life cycles span millions, billions, even trillions of years. Over time, they evolve, changing in size, temperature, and brightness. Some stars live relatively quiet lives like our own sun, while others go out with a bang in spectacular supernova explosions. These explosions can outshine entire galaxies for a brief moment. The type of star and its ultimate fate are determined by its mass. Massive stars may become black holes or neutron stars, while smaller stars may end their lives as white dwarfs. The remnants of these stars enrich the cosmos, seeding future generations of stars and planets. In this way, the cycle of stellar life continues, shaping the universe as we know it. Stars form within massive clouds of gas and dust, known as nebulae. These vast and colorful regions of space are often referred to as stellar nurseries. These nebulae are like cosmic nurseries, providing the raw materials for star formation. They contain hydrogen, helium, and trace amounts of heavier elements, all essential for the birth of stars. Gravity is the driving force behind star birth. It pulls the gas and dust particles together, initiating the process of star formation. Within a nebula, regions of slightly higher density begin to attract more and more gas and dust. These denser regions are the seeds of future stars. This process, called accretion, causes these regions to collapse under their own weight. As they gather more material, their gravitational pull strengthens. As the cloud collapses, it heats up. The increasing pressure and temperature within the collapsing cloud are crucial for the next stages of star formation. The core of the collapsing cloud gets incredibly hot and dense. This core, known as a protostar, is the early stage of a star's life. Eventually, the temperature and pressure at the core become so intense that nuclear fusion begins. This is the process that powers stars. Hydrogen atoms fuse together to form helium, releasing enormous amounts of energy in the process. This energy is what makes stars shine so brightly. This energy release prevents further gravitational collapse and marks the birth of a star. The star enters a stable phase, shining brightly in the cosmos for millions or even billions of years. Our Sun is a relatively average star. It's classified as a yellow dwarf star. The Sun is about halfway through its 10 billion-year lifespan. It's composed mostly of hydrogen and helium, the two lightest elements in the universe. Inside the Sun's core, hydrogen atoms are constantly fusing to create helium, a process that releases the energy that sustains life on Earth. This energy travels outward from the core, through the Sun's radiative and convective zones, eventually reaching the surface as sunlight. The Sun's surface temperature is about 5,500 degrees Celsius, which is 9,932 degrees Fahrenheit. While this seems incredibly hot, it's actually cooler than many other stars in the universe. Stars come in a variety of sizes, temperatures, and colors. They're often classified by these characteristics, which are largely determined by their mass. Our Sun is considered a dwarf star, but even smaller and cooler stars exist, known as red dwarfs. Red dwarfs are the most common type of star in the Milky Way galaxy. Larger and hotter than our Sun are the blue giants. These stellar behemoths burn through their fuel much faster than smaller stars, leading to shorter but more dramatic lifespans. Red giants are stars that have exhausted the hydrogen fuel in their cores. They expand significantly, becoming much larger and cooler than they were in their main sequence phase. In about 5 billion years, our Sun will exhaust the hydrogen fuel in its core. Without the outward pressure from nuclear fusion, the core will begin to contract under its own gravity. As the core contracts, it heats up, causing the sun's outer layers to expand dramatically. The sun will swell to become a red giant, engulfing the orbits of Mercury, Venus, and possibly even Earth. Eventually, the sun will shed its outer layers into space, creating a beautiful planetary nebula. The remaining core will be a small, dense object called a white dwarf. White dwarfs are incredibly hot but no longer produce energy through fusion. They slowly cool down over billions of years. Red dwarfs are the smallest and coolest type of main sequence star. Despite their diminutive size, they have incredibly long lifespans. Because red dwarfs have lower masses, they burn through their hydrogen fuel much more slowly than larger stars. In fact, red dwarfs are thought to have lifespans of trillions of years, far longer than the current age of the universe. While red dwarfs are too faint to be seen with the naked eye, they are incredibly common. It's estimated that red dwarfs make up about 85% of the stars in the Milky Way galaxy. Their longevity and abundance make them fascinating objects of study for astronomers. Red giants and blue supergiants represent later stages in the lives of stars much more massive than our Sun. When these stars exhaust their core hydrogen fuel, they begin to fuse heavier elements, such as helium and carbon. This process releases even more energy, causing the star to expand dramatically. Red giants are cooler than their blue supergiant counterparts, giving them a reddish hue. Blue supergiants are incredibly hot and luminous, some shining with the brilliance of millions of suns. These stellar titans live fast and die young, their lives measured in mere millions of years. Their massive size and intense energy output make them prime candidates for supernova explosions. Supernovae are among the most violent and energetic events in the universe. They occur when a star reaches the end of its life and can no longer support itself against gravitational collapse. There are two main types of supernovae. Type 1 supernovae occur in binary star systems where a white dwarf pulls material from its companion star until it reaches a critical mass and explodes. Type 2 supernovae involve the death of a massive star, typically a blue supergiant. As the star runs out of fuel, its core collapses, triggering a shockwave that rips the star apart in a cataclysmic explosion. Supernovae are so bright that they can outshine entire galaxies for a brief period. After a supernova explosion, the core of the star is compressed to incredible densities. If the core is less than about 3 times the mass of the Sun, it will form a neutron star. Neutron stars are incredibly dense objects, packing more mass than the Sun into a sphere only a few miles across. If the core is more massive than 3 solar masses, gravity will overcome all other forces and the core will collapse into a black hole. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are among the most mysterious and intriguing objects in the universe. Supernovae are not only destructive events but also crucial for the evolution of galaxies and the universe as a whole. The intense energy released in a supernova explosion disperses heavy elements, forged in the star's core, into the surrounding interstellar medium. These heavy elements are the building blocks for planets, moons, and even life itself. The shockwaves from supernovae can also trigger the formation of new stars by compressing nearby clouds of gas and dust. In this way, the death of one generation of stars paves the way for the birth of new stars and planetary systems. Supernovae are essential to the cosmic cycle of stellar death and rebirth. As we gaze up at the night sky, we are filled with a sense of wonder and curiosity. We are witnessing the life and death of stars across vast distances and cosmic timescales. These celestial events unfold over millions, sometimes billions of years, far beyond the span of a human lifetime. The atoms in our bodies were once forged in the cores of stars that lived and died long ago. Through the process of stellar nucleosynthesis, elements like carbon, oxygen, and iron were created, which are essential to life as we know it. We are literally made of stardust. This cosmic dust scattered across the universe eventually coalesced to form planets, including our own Earth. Understanding the life cycles of stars allows us to appreciate our place in the grand scheme of the universe. From their fiery births in nebulae to their explosive deaths as supernovae, stars play a crucial role in the cosmic order. We are part of a vast and interconnected cosmic web. where the birth, life and death of stars drive the evolution of galaxies and the creation of the elements that make up everything we know. This intricate dance of matter and energy shapes the very fabric of the cosmos. The study of stars is a journey into our cosmic origins and a testament to the incredible forces at play in the universe. By exploring the stars, we not only learn about the universe, but also about ourselves and our place within it.